Okay, for chapter 4, we're going to be doing a lot of probability and counting rules. So everything's just kind of how we've always thought about probability before. It's kind of like the basic things that we've done a little bit. Maybe? Okay. So for sample spaces and probabilities, we're going to go over our basic ideas. Our probability experiment is what we call the chance process that leads to well-defined results called outcomes. So outcomes, we'll talk about a lot about outcomes. A trial is when we're doing like a single experiment. So, okay, I'm going to flip this coin. What am I going to get? Is it going to be a heads or a tails? That's a single trial. Okay, then when we're doing like a probability experiment, we're probably doing multiple trials. We're doing multiple coin flipping kind of things. Outcome is the result of a single trial of the probability experiment. So we'll talk a lot about outcomes. We'll just use all these words. Sample space is all of the possible things that can happen. So if I'm flipping a coin, what is my sample space? Oh, it's heads or tails. Those are the only things that can happen. Okay, so these are just like examples. So experiment, toss 1 coin, heads, tails. Roll a dice, I can have 1, 2, 3, 4, 5, 6. Answer true or false question, my sample space is just true or false. The weird thing that we get into that we'll actually be doing more of is what if I toss 2 coins? What are my possibilities there? So I could have 2 heads, I could have 2 tails, I could have a heads and tails, or I could have a tails and a heads. Okay, so we'll have to think about like all the different orders that these can possibly happen in as well. What? Is that gonna make you mad? No? No. Okay. So, sample space, all the possibilities together. So let's find the sample space for rolling 2 die. So whenever we have to do these, it will take up like a lot of room. It's usually not like tons of thought. Just make sure you're nice and ordered whenever you're doing these things. Okay, so things you'll also do is after we get done listing these, we'll also kind of explain what it looks like in words. So if I have rolled 2 dice and I get 1s, we're just going to write them as ordered pairs. So 1, 1, 1, 2, 1, 3. If I roll 2 dice together. So
those are just all the possible outcomes.
Yep.
Okay.
So since there's 6 this way and 6 this way, there'll be 36 things to list. Okay? Yeah. It takes up room. Again, it's not like that hard. It shouldn't be hard for you to do though. Okay? It doesn't really matter if you're putting parentheses or anything around there. It's not crazy. So 1, 4, 1, 5. Just make sure you can keep it ordered for yourself, and somebody else looking at it could tell what you were talking about as well. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Okay? So then we're doing this all again. So 3, 1, 3, 2. Keep this. Make sure I would write this down, or at least feel comfortable with it enough, because there will definitely be questions about this, and it's kind of ridiculous to make this, what's the probability of getting a 5 and a 4 together? So 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. 5, 1, 6, 1, 5, 2, 6, 2, 5, 3, 6, 3, 5, 4, 6, 4, 5, 5, 6, 5, 5, 6, 6, 6. Okay, so that's kind of what you're doing when you're making these things. So then, okay, how many actual outcomes were in my sample space? 36, I can count those. So any of the probabilities that we're doing then, we're writing them out of 36. So if I asked you, what's the probability of getting a 4 and a 1? So what that would look like is probability of a 4 and a 1 together. How many different things have a 4 and a 1? So there's actually 2 things. So when we're actually doing those probabilities then, we're going to look at our table to find those, and we're going to say 2 out of the total of 36. Always reduce things as much as you can. I like to see both answers. I like to see the original thing, like what it looked like from the original amount of data, and then the reduced thing. That way I can tell, make sure you're counting in the right place. Because if you just we're like, oh, 1/6, then I just made up a number. I don't know if you're thinking about, oh, there's 6 numbers on a dice, or I don't know if you're thinking what kind of stuff you're thinking. And I like to kind of have an idea of what that's doing. Okay, next thing we're gonna do, we use these a lot for. It's just reduced it. We're gonna also do what is the probability of drawing 1 card out of a deck. When I'm doing the sample space for that, I'm listing all the possibilities. I don't actually want to write those all out, so I put in a nice picture, okay? All the possibilities is ace of hearts, ace through king of hearts, ace through king of diamonds, spades, clubs. I can't think of anything. Okay. For this chapter, be really familiar with the names of all of the hearts and clubs and diamonds and spades. Okay. So when we describe things in words, what we're going to do for the words is we're going to say 4 possible suits, each with values A through K. So there's 13 actual numbers or card values. So be good using words to describe things as well. Okay, let's find the sample space for 3 children. So what is the sample space if I had 3 children? So what you're going to do for those guys is list them all out separately.
And that's the sample space?
This right here is the sample space. So I had...
Sample space is just how many numbers are in the sample?
It is like all the possibilities. So I could have had a boy, boy, boy. I could have had a boy, boy. My third one was a girl. Could have had a boy, girl, boy. So it's kind of like the order that they could have happened in. And we need to care about that when we're doing those kind of things. Oh, whoops. Nope. Okay. So right here, I just wanted to say that it's easy to list, or whatever. Well, whatever you're having, whatever kind of things we're listing. It's easy. We only had boy and girl. We didn't have anything really crazy. So what I'm going to do is kind of, have you guys ever made a tree diagram? I was going to call it a diagram tree is what I was going to call it. So let's do that. Wow, that was like so fast on their clicking. So what I was going to do is go through that for the boys and girls for 3 kids. I think so, yeah. So if we make it for these 3 children, we start off with, the weird part is that I make my first little branch of my tree from nothing.
Yeah.
Okay? What's my first possibility for my first kid?
Boy, boy, boy.
No.
Oh, boy.
Boy or a girl. Now for my second kid, what were my possibilities? Also a boy or a girl, it didn't change. Also a boy or a girl down here. Even if I had a girl first, it wouldn't have mattered. Now I'm going to do the same thing for my third kid. And all this does is kind of make it really nice to organize your stuff so that you don't forget anything. Because sometimes it's weird and you just, oh, I already listed that, but you really didn't because you, yeah. So I could have had boy, girl, one other boy, girl, okay? Okay, so if I follow this along here, if I listed my first thing, it's boy, boy, boy. Okay, if I went my first thing again, so my second thing would have been boy, boy. Okay, I already did that one, so now I'm going to go to girl. Okay, and again, for these 3 things, it's usually pretty easy to actually list them and go through this kind of step in your head. So if I started off with a boy, then I could have had a girl, and then I could have had a boy, but I also could have had a girl. So that takes care of those guys. So all this is just helping you list things. I could have started off with a girl. I could have had a girl, boy, boy. And that was kind of like this line here. I could have had a girl, boy, girl. Okay, then I could have had a girl, girl, boy. Yeah, and 3 girls, then...
I mean, 2 girls.
Ugh. Okay, so that gets all the possibilities. If you're kind of listing them, though, it's usually not too bad for these little guys. Okay? Okay? That's why they quit, Taryn.
They're like, no more.
Okay, so an event consists of the outcomes of the probability experiment. A simple event would be something for that single trial. Okay, what are the chances of rolling a 6? Okay, then we get into what we call compound events, and they are basically just multiple simple events. An example of that would be rolling an odd number. How many odd numbers are there on a dice? So there's 3 odd numbers, so we actually have to add those guys together. Okay, and the next section we're going to be talking more about those addition rules for, whoops. I need to like start putting like a shape or something at the end so I know I'm done. It's like,
Square. Stop.
yep, that's what I should do. I'm thinking about it. Okay, and this is just kind of so I can use these words and we know what we're all talking about. Okay, there's 3 basic types of probability, and we're going to go over these a little bit each right now. Classical, empirical, and subjective. I was going to say, I don't know what I was going to say, subjective. Subjective. So classical is where we think of what's the chances of getting a heads or a tails? 1/2 usually, right? That's usually what we say. What's the chances of getting a girl or a boy? 1/2, but it's really not 1/2. What? No, it's about 49% and 51% for the girls and boys. The boys are slightly higher. So that is what we call the empirical probability. That's what actually happens. No, and it doesn't happen with anybody.
75 to 25.
Oh, they just had 3 kids.
Yeah, but it was like 75 to 25 for getting a girl because, or getting a boy, because they just kept getting girls and then they finally got a boy. I really don't think it was 51-49 for that.
No. Classical probability, we always think of everything having the same probability of occurring. So things don't change. This is really blurry, huh? The probability is the number of outcomes that actually happened over the things that are in your sample space. Okay? So the one on top is the ones you were talking about, the ones you wanted. Wanted over basically the number of possibilities. The number you wanted over the number of possibilities. What are you doing? It's gross. Yeah, it's gross. Okay. So those guys are your classical probability. So kind of in the book it talks about, okay, for that 50-50 chance, we can say 1/2, we can say 0.5, we can say 50%. One of the things that your book goes into later is that, oh, actually it might be on a slide. I can't ever remember what I put on a slide after I made them a few days ago. Okay. Maybe let's try again. Okay. Rounding rules for these classical probabilities, or just in general. Rounding rules. So if I have something really, really tiny, I'm gonna just round to that first thing that's not a 0. So I'm gonna round to that spot, so that becomes a 6. Okay, don't care about that. So just kind of, those only work for really tiny things. I can't just say, oh, okay, which, I don't, I'm trying to think of other little tiny things. I'm trying to think of one that it wouldn't work for. Okay, make sure you have a few zeros before you try to round like that. Most are expressed with a fraction or a decimal. The weird thing is percentages are not considered probabilities. But if I say 50%, how many, like you guys are good enough to go back and forth to be like, oh, I can write it as 50%, or I can also say 0.5. Same deal. You guys know those percentage rules enough that we can use them like that. So I just generally don't want you to write them in percentages. I will try not to as well. Okay, find the probability of getting a black card, a black 10 from a deck of cards. Sorry, I'm reading. Whoops, okay, look, we're actually doing that one now. I really need to put like a shape or something there for me. You're gonna kill me. You're just trying to kill me. Okay, so I want to look at how many black cards were there on those things. Really, yeah, you're trying to kill me, huh? So I could have like an ace, 2, 3, 4, 5, 6, 7, blah, 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 all the way to a king. How many black 10s are there in a whole deck of cards? Okay, so there's 2 black 10s. So there is a 10 of, I don't even know how to draw a spade. Spades. This is just looking worse, huh? Or I could have a 10 of clubs. Let me see if I can draw clubs too. Oh my God, you guys, focus, math. Okay, so there's 2 out of how many total possibilities? 52. Okay, get used to this notation that we're probably like, I wrote this out in words. How you would also usually see this is probability of a black 10. And then you would write out 2 out of 52. 1/26. That's because you're supposed to be doing math.
Mine had nothing to do with Maddie in it.
Mine had a bunch of stuff to do with you and Maddie, and I'm like, I don't know why mine had so much to do with Jason.
Look at this math. Oh my gosh. Math. Okay, using sample spaces. So we've created those sample spaces for those boys and girls for 3 children. What's the probability that 2 of the 3 children are girls? Okay, so I'm going to list them out again. I probably should have just put them there. Okay, cool.
BGB, BGG, GBB, or GBG, GGB, GGG. Dude, you're going too fast. No. What?
How many do I have now? I don't have a girl. 2, 4, 6, 8. Okay, so there's 8 total possibilities. How many of these have only 2 girls? So I don't care about 3 girls, don't care about 3 boys. That one doesn't. So you're just counting how many of them have 2 girls.
3 of them do.
That one. Okay, so there is 3. How many total possibilities were there? 8. So the probability of 2 girls is 3 out of 8. I can't reduce it, so I leave that like that.
And we win.
Okay, so basically that number on top is just the number of things that you wanted. Over the bottom was just how many you total had.
Terrence's mind today? Terrence thinking of inappropriate things.
Don't be like that,
I
Taryn.
copied the top one, so instead of putting 2 girls, I put black girls.
Okay, general rules, which you guys should always already be a little bit familiar with. The probability of any event, so remember that's just how we wrote that, was the probability of, I don't even know what we were going after, 2 girls. Okay, so an event can just be anything that we're actually wanting. That's what E is usually representing. Is always between 0 and 1. That's why when I say 50%, oh hey look, 50% is 50, not 0.5. 0.5 is between 0 and 1. Okay, it cannot happen if P equals 0, P of E equals 0. So if it just cannot happen ever, if it's certain to happen, the probability is 1 or 100%. Okay, all the probabilities added together is equal to 1. Okay, complements. Complements are not crazy hard. Like when we think of complementary for like a shape. So the complementary here would what adds to 50 or what adds to 90. 50 would make that add to 90. Here our complement is always adding to 1. Okay? Complemented event is a set of outcomes that are not included in the outcomes of this. So we call that E bar. It's written like this with a bar on it. E bar, but it has that. Okay? Find the complement of each event. Rolling a dice and getting a 4. So our sample space, 1, 2, 3, 4, 5, 6. How many of those are 4s?
1.
What is, okay, that is the probability of getting a 4. What's the complement of that then?
5 out of 6?
So yeah, so the complement, so it would be like probability of E is equal to 1/6, but then the probability of E bar is 5/6. Okay, so that's just the notation stuff there. Selecting of the letter of the alphabet and getting a vowel. So what's the probability of getting a vowel? Okay, if I asked you the probability of getting a consonant,
21.
yeah, but would you have gone through and counted all of that, or would you have,
You just take 26.
yeah. So I get 21 out of 26. I subtract those guys. Okay, so 3 kind of things that you can kind of remember how to write them down. The probability of the complement, I don't know why that is just a weird word for me in this sense, is 1 minus PE. Yeah, I don't give a lot of compliments, sorry. Okay, PE is also 1 minus PE bar. Those two added together is always equal to 1. Boy, yeah, you guys are just mean to each other right now, huh? This is just what it looks like on a Venn diagram. It's gross. I guess it's not that gross. But, okay, yeah, it's really. So if I had my PE out here, my P, I guess S is supposed to be their sample space. They just kind of have some weird things going on.
These should be used for like eye tests.
They should be. Actually, I don't know if we would pass them though. Okay, so I just wanted to show you kind of that you can draw these in Venn diagrams. Let's do some empirical probability. They assume certain outcomes are also equally likely, but yeah, that's pretty much what you're gonna do. If I wanted to find what's the probability of getting 1 on a dice, I'm gonna roll the dice, and 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 I'm gonna write down, and I'm gonna make like tally marks. Okay, I had a 1, 2, 3, 4, 5, 6. Okay, let's make my tally marks. Okay, I might have got that. Oh, let's look. But sometimes that doesn't happen. So the probability of flying when we actually look at data, so empirical is kind of actually when we have data to look at. Okay, that's what we usually do unless we're working with cards or dice. Okay. What's the probability of flying? Okay, how many total things were they? So we add them up. What was the thing that I had? So the probability of flying is 6 out of 50, 3 out of 25. Is that all the further it goes? Okay.
25 somehow goes in 33 goes into 25 now.
It does not. Okay, so our formula whenever we're using empirical probability is the frequency for the class, so this was our frequency for the class, over our total frequency in the distribution. Okay, big gross words means same thing that we've kind of been doing there. Using lots of these guys. Okay, hospital stays for maternity patients. Hospital records indicate the knee replacements. Patient stayed in the hospital for a number of days shown in this distribution. Find the number of people that stayed exactly 5 days. So how many people stayed exactly 5 days? So I'm going to just do like little a. So 56 over 127. I'm not going to reduce them just so we don't take up too much time. Okay? If I do the probability of whatever my B thing is, a patient stayed less than 6 days. So how many days were less than 6 days? 3, 4, 5. So what I have to do is I have to add those together. So 15 plus 32. So if I wrote it all out, it would look like this. You don't have to write out this much work. 56 over 127, and then actually add all those numerators up, which I don't feel like doing that right now either. A patient stayed at most 4 days. So if they stayed at most 4 days, what things am I actually caring about? 5. Am I reading it wrong? Does that make sense? 4, 5, 6.
Wait, where is that question?
Oh, no, it would be 3 and 4.
3 and 4. So the probability of C, so sometimes what we do is we write out, okay, that's actually just the probability of 3 happening plus the probability of 4 happening. And so that would be 15 plus 32. So 47 out of 127. Okay, a patient stayed at least 5 days. So where is at least 5 days? That one's the 5, 6, and 7. So if I did the probability of D, it would really just be the probability of 5, 6, and 7. Add those all up. 56 plus 19 plus 5, all over 127.
Do we have to write it like that?
No,
Okay,
no.
so I was like,
No, I just want to make sure that you can see where it's all coming from. No, I don't write it all out like that. I wouldn't expect you guys to either, I don't think. Okay, law of large numbers. So if I roll a dice 6 times, what do I expect to happen? A different number each time, but is it any different? Are my chances of getting a 1 different than from the last time I rolled a 1? No, so I still have equal chances. So what happens is that I have to roll my dice more than probably 6 times. If I only roll my dice 5 times, I'm not even going to be able to get all 6 numbers. Okay, so what I have to do is I have to use really big numbers. That's why I said a bazillion times, because that's what it always feels like. Okay, so we expect the empirical probability to approach the classical probability. So that means the more and more that I roll, those frequencies will change. Okay, pit bosses always kind of watch the dice, and they try to see if they're loaded dice or anything, or one of the sides are weighted. So, so that kind of, they expect those classical probabilities to always happen. Okay, subjective probability was that last piece. This is just an educated guess, somebody's opinion. They've probably done a lot of work. Yeah. Yeah, so an 80% chance of an earthquake happening in Oklahoma or Colorado. So it doesn't really matter what it is they're saying, it's just that. What?
blah, blah, blah.
That was a song?
Kesha, that's right.
I missed that completely. What a shame. Okay, a doctor might say that I think 30% of my patients that I see come in here. Okay, that might be true for them, but that really might not have the data to back it up. Okay, we use probability in risk-taking types of things. So something in your book that I thought was interesting is people tend to overestimate accidents and weather. So like we really like over-prepare for those types of things, right? And we actually underestimate heart attacks. Generally, people that were questioned, okay, like what's your chances of dying of a heart attack? People would like, I don't know how exactly they did the survey. So, but it said that people, it seemed like about 1 in 20 thought that they would die of a heart attack. but the actual chances of you dying of a heart attack is closer to 1 in 3. So things that we can actually change, that was kind of what I got out of it, is we can change like the smoking and the drinking that changes your heart health, but we really can't change the accident. We can't change those acts of God, okay? Okay? Always find out where your information was obtained. This thingy was obtained from your book, but I don't know where they got it. So, but I still thought it was kind of cool.
Karen dies of a heart
Okay,
attack.
we don't need to do 4 2. Well, she might. I don't know if she will or not.
Yeah, but she's